Okay, well, this is Ron Lewis. I'm the product manager for Teledyne Isco's Flash Chromatography products. I'd like to welcome you to our seminar this morning. And before we get started, one of the things that we'll do is at the end of the presentation, we'll be happy to answer any questions you might have. You can enter those questions at any time using the text box down in the lower right-hand corner of your screen. So when you think of something, just type it in, and then it will accumulate those, and at the end of the presentation, we'll go through those questions. So we'll go ahead and get started here. This should take about an hour, and hopefully I've timed it to where it won't run longer than that. One of the things that we wanted to talk about was just cover the fact that reverse phase flash is greener than normal phase flash, and some of the reasons for that are because that the flash columns can be reused. Typically in normal phase flash, columns are used once and disposed of. Reverse phase is a little different. As long as they're properly stored, they can be run multiple times, which leads to less material going to the landfill, less hazardous waste to be cleaned up. Lowers the carbon footprint because typical mobile phases are water and methanol instead of hexane ethyl acetate. So large amount of water, a small amount of an organic modifier is typically what's used in the C18 or reverse phase flash chromatography. The other thing that you can do is you can actually increase your throughput, increase the purity of your sample, while being in a green environment. And our gold RF columns that we're going to talk about a little bit later is one of our options. They run higher efficiencies, which means that you can get higher loading, and higher loading means less solvent required to purify your compounds. We're going to try to cover several topics briefly today. We're going to talk about a little bit about flash versus prep, because once you get into the reverse phase purification, that's been traditionally dedicated to preparative HPLC, and we'll show you some examples of comparisons of the two techniques. We're going to cover the different reverse phase options that are available from Teledyne Isco. We're going to talk about how you choose the right media for your application. Touch briefly on scale-up and the effects of modifiers, as well as when to use non-aqueous reversed phase, which is a very powerful technique. This is an example of a sample that was a peptide. It was generated by one of our universities here in Nebraska. We ran it in two different types of reverse phase columns, what we call a Redisep Rf, which is our standard product, and also we ran it on Redisep Rf Gold C18. Both of those columns are C18. In this particular case, we also ran on a preparative system using a Vidac column. That's a 10 by 250 millimeter. So we did a purification by HPLC. We used two different reverse phase columns that were dedicated to flash. What you'll see here is that we ran on the C18 column, we ran a 10 milligram sample load. Run time was 20 minutes. This don't be confused by this time axis down here. This is actually column volumes, and we're running at a speed fast enough that in about 20 minutes we cover the 50 column volumes in that time frame. And we used a 13 gram Redisep C18 column. Down below, we injected on our Rf Gold C18, we injected 46 milligrams of sample, and we used a 15.5 gram Redisep Gold column. Over here on the upper right-hand side is the chromatography using a Vidac 5 micron column. We again injected 10 milligrams of sample. Runtime was 60 minutes in this particular case. And the column volume of this Vidac column was very similar to that of the 15.5 gram Redisep Gold. What you can see here is that the Redisep Gold, we had very nice separation, very good peak shape between the impurities and the major peak of interest. And since we were able to run this in 20 minutes and inject, which is 3 times faster, and inject at least 4 times the amount of material, we really ended up with about a 12x productivity increase. So, very good example of how efficient Redisep Gold columns are, especially when compared to something like a 5 micron Vidac column, which is one of the standard high quality HPLC preparative column. Well, it's one thing to get peaks, and it's another thing to look at peak purity. So this is the 2 samples that were compared, the Redisep Gold sample and the preparative HPLC sample, and you can see that the purity of the 2 was equivalent. So faster, more material per injection, and equivalent purity between preparative and flash chromatography run in reverse phase. And we're seeing this more and more with our customers. We're seeing a lot of customers that are retiring semi-preparative and preparative HPLC systems in favor of these higher performance columns run in a flash system. To go over, I mentioned two of the options we have. I mentioned the Redisep Rf C18, which didn't give a very good separation in the last example. It's based around our standard normal phase silica, which is a irregular particle shape, and it's between 40 and 63 micron in particle diameter. And then there's the Redisep Gold line, which are spherical material, so spherical particles, 20 to 40 microns in diameter. And in that case we have 2 different sizes or bonded phases available, what we call Redisep Gold C18 and another one which is Redisep Gold C18Aq. We'll talk about the differences between those 2 and when you should choose the Redisep C18 versus AQ in just a moment. I want to spend a little bit of time just covering some of the typical things that you would find regardless of which one of these 3 materials you would be using to do a flash separation in the reverse phase mode. First is purification is in reverse phase is typically involving medium to high polarity compounds. Just some examples: carbohydrates, acids, peptides, heterocycles and ionic compounds, dyes. All of these are good candidates to do reverse phase flash separations with. This is kind of an interesting example. This is a mixture of fluorobromo and chlorochromones. And in this particular case, what you see, this is run on a C8 regular silica column in normal phase using hexane ethyl acetate, and you see that the fluoro, bromo, and chloro all coelute. Run on a C18 Redisep column using water methanol, you'll see that the fluoro compound is separated from the chloro and bromo, which still coelute. So if you're interested in purifying the fluorochromone from the chloro and bromo, reverse phase is a very good option, and you can see the different resolving power that you get between normal and reverse phase on this type of ionic compound example. Again, regardless of the material, whether it be Redisep or Redisep Gold, C18 columns are shipped dry and they need to be reconditioned before use. To do the conditioning, the first thing is to flush with 6 column volumes of 1:1 water acetonitrile or 2 column volumes of 100% acetonitrile just to get the surface wetted. C18 columns can be used at least 30 times with proper use, and obviously this is going to vary based upon purity of the sample that you are purifying to begin with. If it's got a lot of non-polar impurities in it, then that may be retained on the C18. That might reduce that time, the number of times that you can use the column. Also depends that they're stored properly. But as a general rule, you can get at least 30 purifications prior to having to dispose of the column. And columns should be stored in 70 to 90% of the organic solvent, so either acetonitrile, methanol, or ethanol. Doing these storage will keep the column wetted and also keep the column cleansed of material impurities that might build up. When you're running the flash system, one of the things that you might see is this would be a typical C18 Run Profile, where you start off with an initial 10% B in water, ramp up to your gradient in the separation, and then go through a column wash where you go to 100% of your organic, and then either equilibrate back to the 10% B, or if you're going to store it at the end of the run, simply program your flash system to go back to 80% B and condition the column there for storage. Some of the benefits of reverse phase flash chromatography are the fact that you use the same equipment that you have for normal phase flash. It's been designed to be easy to use, simple to program. The columns are low cost, and I know that everyone's going to say, well, the columns are not as cheap as silica, which is a single-use column for flash, and that is true. But when you compare the cost of a reverse phase flash column to that of a semi-preparative or preparative HPLC column, you'll find that there's a significant cost savings with reverse phase flash cartridges. You can typically get higher loading capacities than in HPLC. Loading capacities obviously depend upon how well the material of interest is separated from its impurities, but sample loading can vary anywhere from 0.1 to 2%. You can also expect to get purities or recovery of greater than 85%. Many times in flash, the recovery percentages are higher than that you find with reverse phase HPLC. And it also reduces the volume of organic solvents that are consumed during the purification process as composed to normal phase flash. Let's talk a little bit about solvent substitution. These are some general guidelines that you can follow. And this is a nomogram which is produced for, found in the literature for substituting common solvents for C18. What you see here is you see the percentage of methanol in water percent methanol, or percent acetonitrile in water, excuse me, the percent methanol in water, and the percent THF in water. And if you draw a line here, this is a general guide. 40% acetonitrile in water gives you the same elution strength as about 50% methanol in water, or about 30% THF. So if you're running an isocratic separation and you found that 40% acetonitrile in water gave you good retention times, then if you wanted to substitute to a less expensive solvent, you can switch over to methanol and increase to about 50%. You can see over here on the right in this box, you can see the chromatograms for sample of two different components at 40% acetonitrile water, 50%, the retention times for the second peak is a little longer, 30% THF, and so these are guidelines, as I mentioned. We increased the organic composition of methanol and THF by 5%, and that's what you see down here in the bottom center of your screen, where the retention times now line up very nicely for that second peak simply by adding another 5%. But you can see that this chart is very useful, and it got us very close to retention times that were equivalent, so we could change from one solvent to another in the reverse phase mode and get very close to the right retention times. Same thing can be done with switching solvents during a gradient run. If we take that same example, and here we have our 40, 50, and 30 lines, what we can do is we can end our run earlier once our compound of interest has eluted. And what this is showing is that you can use the nomogram to pick not only you can pick the starting percentage of B, you can also pick the ending percentage of B. And so in this particular example of these same three components, we started at 5% B. We did a acetonitrile gradient that ended at 95% B. Everything came off during that time window. And that 5% B is equivalent to about 95% methanol, according to the nomogram. It's equivalent to about 69% THF. So these gradients were from 0 to 95 for methanol and acetonitrile, and 5% to 95% acetonitrile and methanol, and 5% to 69% THF. And so the gradients were run over the same time window, but just at different slopes because of the amount of percent B that was used during the purification. I've got a note down here that is a warning that some selectivity changes can be seen, and that's primarily because of the different selectivity that you get between when you go from acetonitrile to THF. There is some selectivity differences that are caused by the organic modifier. Now, if you need to develop your method in reverse phase flash, there's really three techniques that are commonly used. One technique is to determine the preferred mobile phase using reverse phase TLC plates. And at Teledyne Isco, we sell a set of reverse phase C18 plates where we can develop the conditions that can be transferred directly from the TLC plate to the flash reverse phase column. You can also use analytical HPLC to develop your conditions, or you can use a 5-gram Redisep C18 column to actually develop the method and reduce your solvent consumption while you're developing your method. If you choose to do it on HPLC, you simply do some gradients using water methanol with a standard analytical C18 column, And what you'll find is that if you're running a CombiFlash Redisep Rf C18, which is the standard irregular particle size, you need about 30-second baseline resolution between your peaks to get good separation and purification on a Redisep C18. Likewise, if you're using a Redisep Gold C18 column, you need about 10 seconds of baseline resolution between your components to get your purity. So that's some general rules that would apply to Redisep C18 or Redisep Gold C18 or Redisep Gold C18Aq. Let's just talk a little bit about the Redisep Gold product. Redisep Gold is the highest, gives you the highest performance flash columns, and the material is 20 to 40 micron particle distribution. It has a 30 micron average particle size, and that's standard than the smaller than the standard 40 to 60 micron flash silica, which has about a 50 micron average. And the columns are all packed with this with these 20 to 40 micron spherical silica gel, which is preparative HPLC quality material. So all of your preparative HPLC columns today are spherical silica material. Why spherical? Well, there's one thing is the particle range is typically particle size range is typically smaller. Particles pack more densely together, and they reduce the, if you can look at these irregular particles here, they are pretty jagged, so when they're packed in a column, they don't necessarily pack uniformly, and so there can be fairly large gaps, which is termed interstitial volume. The spherical particles pack closer together, they're tighter, they're more consistent in size, and so that reduces the interstitial volume and contributes to higher resolution. And the other thing that's critical to point out here is that when you're packing irregular particles, there's no way to prevent the fact that rough edges, some of these rough edges might break off, create fines during the packing process that will actually end up creating problems in some cases if it generates enough fines to clog your frits and build up back pressure in your column. Spherical material doesn't have that problem, so you have minimal back pressures, and that's one of the reasons why you can run smaller particles in flash without increasing your back pressure on the column, because of the lack of fines being produced during the packing process. Here's one example of what the difference between our standard Redisep C18 and our Redisep Gold C18. What you can see here is there's this one peak that has tailing here on the standard C18 material, whereas on the Gold C18 you have very nice resolution, and you can see there's 3 distinct compounds that would be otherwise just one component here. So you can actually start to get some purification by cutting these into different peaks. Another example that we touched on a little while ago, this is a peptide that was produced at Creighton University in Omaha, here close to Lincoln. And this was the purification that I showed you earlier, where we've got Redisep Gold, and you can see that there's a distinct separation between the impurities and the major component. And as I mentioned earlier, you end up with, in this particular example, equivalent purity to that of what you would get off of your preparative HPLC system. Now, another thing with that's unique with the Redisep Gold silica, C18 silica, is the fact that it's stable over a large pH range. And there's some compounds that are typically purified in reverse phase mode will have multiple ionic species. And what that means is that they're kind of in equilibrium between a charged compound and a non-charged compound. When this happens, you end up getting gets broad peaks, and you get lower resolution because of that. Typically, users will add trifluoroacetic acid or TFA to lower the pH and drive this equilibrium that exists between a charged and a non-charged species in one direction or another. By adding trifluoroacetic acid, you typically drive it back to the charged state if it's an acidic compound. However, if the compound happens to be acid sensitive, you are better off to do the purification under basic conditions. Most C18 silica gels aren't stable at a pH greater than 7.5. Around pH of 8, you start to see silica dissolving. That's if it's unprotected. And no matter how much bonding you do to the silica, you still end up with some places on the surface of the silica particle that are unprotected and can cause start to degrade over time. However, we have done studies that show that the Redisep Gold silica is stable up to a pH of 10. Let me give you an example of that. This is 20 purifications that we ran at pH 10, separating theophylline from caffeine. And what you'll see is for about the first 17 injections here, we have essentially the same chromatographic results. At 17, 18, 19, and 20, you start to see degradation of the theophylline, and at that point in time, the column has beginning to lose its resolving power, at least for that component. Now, if you were not interested in purifying the theophylline, but were only interested in purifying the caffeine, even after the 20 samples are run, you still see that you have very good peak shape on the caffeine. So this column could continue to be used past the 20 purification runs, where we're using ammonium hydroxide as the modifier at pH of 10. So pretty extreme conditions. One of the reasons that this is capable of, the Redisep Gold is capable of doing this, is because of exhaustive end capping that is undergone after the C18 moiety is bonded to the silica backbone. We then begin to end cap the residual silanol sites, and we continue that to get a maximum coverage of the silica. If you were to use a Redisep Gold C18 column at pH 10 to do this purification that we just illustrated, the column will begin to degrade with prolonged exposure, as we mentioned. But it's fairly simple and straightforward to flush the column and store the column under a neutral solvent to maintain column life. So you can wash with a minimum. To do that, you need to wash with a minimum of 5 column volumes of methanol to make sure you get all of the ammonium hydroxide modifier off the column, and then store the column under the conditions we mentioned earlier, but with 80 to 90% organic modifier, either methanol, acetonitrile. And By doing so, you can keep the column stored indefinitely without further degradation. So we've been talking so far about Redisep Gold C18 and Redisep C18. The third product that we offer is what we call Redisep Gold C18Aq. And the most frequently asked question is, when do I use that column? A couple of general guidelines. One is if you're dealing with compounds that elute with less than 50% organic solvent during your purification process, that's a good candidate to use a C18Aq column on. And this other statement here says kind of the same thing, compounds that elute with very high concentrations of water. We occasionally get a customer that calls in and says, I've injected my compound on my C18 material and it came right off. It wasn't even retained on the column. That's definitely a case where a C18Aq should be used, because with 90% water or greater than 90% water and you don't have any retention, then the AQ is a good choice. The reason for that is because of the way that the AQ has been bonded. Typically what happens is that you have these large C18 moieties that are attached to the silica surface. And as you have methanol, water, acetonitrile, these moieties are stand up and form what is normally referred to as a brush. So as the sample comes by, it interacts with this long chain hydrocarbon, and that's what causes the separation, is how well your compound reacts versus the impurities react. And if you get a low enough percent of organic modifier, you all of a sudden don't have these C18 moieties solvated, and they collapse onto the surface. And so this is what's called phase collapse. And so when you have this collapse, you don't really have a lot of interaction between your C18 chain and any compound that you might inject. So the compounds, once the phase collapse happens, generally elute quickly off the column because there's very little interaction. There's proprietary techniques that's used on bonding the C18Aq to the silica surface so that these brushes will stand up even in high concentrations of water. So going below the 10% line that we had kind of set up earlier is a perfect scenario for using the C18Aq. So again, 20 to 40 micron material. You can start your gradients at 0% organic, and compared to what we're saying is 10% is a minimum for the standard Gold C18 or the standard Redisep C18. If your compound doesn't elute until it gets above 50% organic, then you really need to go back to the standard C18 column. Things that are used, probably the most common one is water-soluble dyes. Anything that's highly polar and water-soluble, but water-soluble dyes is our most common use. Glycosated compounds, peptides, nucleotides, all are good candidates for C18Aq. This is an example of a dye that's separated, and it's comparing the Redisep Gold C18 versus Redisep Gold C18Aq, and you can see how much more resolution we have. The blue line in this case is the Redisep C18Aq, and you can see how much more separation we have, and it's actually the materials are retained longer under the same gradient conditions. And so a good reason to use a C18Aq column. And this is another example. Here's the C18Aq. You can see where this peak has a much higher response than the Redisep Gold C18, which is this component here. But this is 3 times the loading between these two. So we loaded 3 times as much compound onto the C18Aq as was loaded onto the standard C18. And so you can see that we got excellent resolution. They were run under the same gradient conditions for the 2 compounds, and they were the same size columns. So much better resolution using the C18Q for a water-soluble dye. Let's switch over now and talk a little bit about scale-up. This is just one simple example where here's a chromatogram that was run on a 12-gram Redisep Gold C18, and we ran our sample, and then through a series of steps we transferred that method over to a 750-gram column running on a different instrument that's manufactured by Teledyne Isco. And we've made some additional changes where we've changed the wavelength that's being monitored, but at the same time you can see where the gradient profile is the same. In this case it's a rather unique non-aqueous reverse phase where we're running from methanol to dichloromethane, and so this kind of taxes everything. It's a little bit different C18 column where we're using non-aqueous reverse phase instead of the standard water methanol or water acetonitrile gradients. We're using all wavelength detection to find components where we maybe didn't have the wavelength set correctly. And so we've done a number of changes, but all very simple. And I'll show you just how simple those are in just a second. This is just kind of an example of maybe doing a preparative method development where you would start off with a 4.3 or 5 gram C18 column, run maybe 10 milligrams of sample, work out your separation, and then it can simply be scaled up. And here's where we've started off with 10 milligrams, scaled it up through a series of columns, and are actually running it on running 7 grams on a 360 gram column. And so we can eliminate several of these steps as I'll show you here. But first, just want to point out that samples are easily scaled up from 40 milligrams up to 300 grams by using a 4 gram to a 3 kilogram column. The tricks are to maintain the same sample loading, in other words, the same weight % of sample on each column, and the sample loading technique should be consistent from one separation to another. So if we were to do a scale up, first thing we would do is we would work out our conditions on a 4 gram column, and then we would take that 4 gram column on our RF200, and you would change the method. You would convert the method to a 330 gram column method. And by doing that, well, all you do is you take your method and you save your method as, and you would choose the 330 gram column. You'd then move that 330 gram column method from the RF200 over to the Torrent, open the method again, and then you would have additional options here, and you would choose the 3 kilogram column if you wanted to, and save the method again. And by doing so, you've taken a run that you perfected on the 4 gram column, migrated it to the 330 gram. The reason you have to go through this step is because the 330 gram is really the smallest column that should be run on a Torrent. And Once you've moved it over to the torrent, you then scale up and save it running at 3 kilo. So you haven't run any samples after you've worked out your method on the 4 gram column, but you've managed to move it over to where you can do a purification directly on the torrent. To just give you quickly some examples, this is the separation on a 4 gram. Method was saved and run on a 330 gram column, and you can see we still have very adequate separation. Now we're injecting 6 grams, almost 6 grams of material. Again, scaled up to a 1.5 kilo column in this case, where now we're running 27 grams of material, and you can see that we still have a very good separation. So very easy to scale up, very quick, no waste of solvents, needlessly to fine-tune gradient conditions. Okay, in the few minutes we have left, I just want to cover two other topics. One, I just want to give you an example of when non-aqueous reverse phase chromatography or purifications might be useful. They're very useful in one of two cases: natural product extraction purification, where you have extracted tea leaves, let's say. You don't know what all's in there, but you want to find out everything that you were able to pull out of the material. Or if you have a totally unknown mixture. I know sometimes reactions go astray where the temperatures go out of line, get too hot. You create this nice black tar, and you want to see what's in the black tar. So you dissolve it up. You don't know what you've got. So non-aqueous reverse phase might be a good example to use there. And this is in the case where a natural product was extracted into ethyl acetate. The ethyl acetate, this liquid was then placed on sea light, and the ethyl acetate evaporated off to do a solid load. And we've kind of done a standard reverse phase gradient. We started off with 10% methanol and water. We ran a gradient up to 100% methanol. And we then switched to methanol and reset our gradient and ran back to dichloromethane. And you'll see that we've gotten several components off here. These are all non-polar material that was in this extract, and you would expect to have quite a bit of non-polar material, but we've got some polar products here, or decreasing in polarity as we go through our gradient under standard reverse phase conditions. And then once you go to non-aqueous reverse phase, you can see where we have an additional set of components that display, or that elute. Another example where typically the same thing, another extract where we start out with 12% water and methanol. We run up to 100% methanol, so we're getting a lot of non-polar products off. And then we run from methanol to 50% acetone, and you can see where we have additional components that come off under those conditions. So if you know that you have a lot of non-polar material, this is an excellent way to make sure you get those off so that you can do your analysis to find out if those are products of interest. Just one comment about the effects of modifiers. When you have compounds that have this nature where you've got an acid function, that acid exists obviously in an equilibrium at some pH where it exists as a non-ionized and an ionized moiety. And this is obviously pH dependent. So as it moves back and forth, you'll see in this chromatogram right here, you'll see where we have this peak at the beginning. And this peak is the ionized compound, so that would be this component that's eluting. Then the next component that elutes would be the non-ionized acid. This is typically not what you want, because people will call occasionally and say, well, I got 2 peaks, I collected them, I ran TLC or I ran mass spec, and both peaks were the same thing. And that's true. In this case, if you collected this peak and this peak, you'd find they had the same mass ion. But so to avoid this, typically you add trifluoroacetic acid, and in that case it drives this reaction back to the non-ionic moiety, so that you get one peak for that one compound. Similarly, you have the same case with an amine function, and in this particular case, if you use trifluoroacetic acid, you drive it to where you have the ionic compound. And so if you're using amines and trifluoroacetic acid, probably this is a good reason why you'd want to consider a C18Aq column. I've got a note down here that acetic acid and formic acid also work well, but for some reason trifluoroacetic acid has become one of the most commonly used ones. Well, now to the commercial. This is the wide range of CombiFlash Rf products that we have. The RF75 here is a 75 psi system, 100 mils per minute maximum. The CombiFlash Rf UV or UV Vis is just that, UV only, UV visible. And then this is the CombiFlash Rf 200i. It has a built-in ELSD and can have a UV ELSD or UV Vis ELSD detector in series. These 3 are all products that run up to 200 mils per minute, 200 psi maximum, and are really the workhorses of our product lines. I mentioned the Torrent in the scale-up. The Torrent is really designed for large purifications up to 1 liter per minute, 100 psi maximum, and is capable of prepping up to 300 grams of material in one single run. Last thing, all of our products are compatible with iPod, iPhones, iPads, so that they can be, if you have a wireless network at your facility, you can monitor conditions, progress of your purification while you're not in the lab over the wireless internet, and you can also make changes to your gradient or react to error messages or status messages that might show up. So it mimics the screen, the peak track screen on our RF systems. So with that, that's all I had to cover today. If you haven't got one, I would encourage you to come in and talk and go into our website and ask for a free book that we've published. So it's Guidelines and Tactics for Flash Chromatography. It covers a lot of the topics that we talk about during our webinars, especially very strong in normal phase flash chromatography techniques, solvent classifications, that type of thing. If you have questions, my contact information is listed here. Thank you very much for attending, and hopefully you found that it was beneficial, and don't forget on the 23rd of August we'll cover a little bit different topic. Thanks very much. Have a great day.